In section 5.6, we are going to be putting a lot of things that we've already done in previous sections together and finding all of the roots for a polynomial function, including any complex roots. So what we need to understand is that a polynomial function that has degree n will have exactly n roots. But that is going to include the real roots, which show as x-intercepts, and the imaginary roots, which do not show up as x-intercepts. Real roots will include any rational roots that you have, including multiplicities, and irrational roots that always go in conjugate pairs. Now, irrational roots are things like x equals 2 plus 5 square roots of 3, and then its conjugate, which would be x equals 2 minus 5 square roots of 3. Now, you can never have just one irrational root. They always go in pairs. And imaginary roots also go in conjugate pairs. Probably not conjugated. Conjugate pairs. So, for example, x equals 2 plus 5i, and then its conjugate, x equals 2 minus 5i. So we have a process that we go through to find all of the roots, and we've kind of already done this when we were listing all the real roots. So to find all of the roots, you're going to start by listing the possible rational roots. And we did this in a previous section. That's where we list the factors of the constant term over factors of the leading coefficient. And then we split that list into plus or minus lots of numbers. If you just want to put a plus or minus at the beginning of that list, as long as you remember that it does mean all of them could be positive or negative, that's fine. That's how we did it before. And then we're going to test using synthetic division. And what we're looking for with synthetic division is that we put our number in with synthetic division, and we're trying to get a 0 down here for our remainder. If the remainder equals 0, this makes our number that we found up here is to be a root. And then that also makes x minus that number to be a factor. And then remember that whatever we get over here is going to be our quotient. So we do list, test. First step, list. Second step, test. Third step, rewrite as the quotient times the divisor, which I guess another way to write divisor would be the factor that we found over here. X minus that number would be our divisor. And then we're going to repeat these 3 steps until the quotient is quadratic, and then we will either factor, use the quadratic formula, or complete the square to find the last 2 roots. So we will go through an example for 2 or 3 or 4 and go through all of those steps. So here's our example, find all roots. So I kind of want to start by knowing how many roots I'm looking for, and that is given by the degree of the polynomial. So I look at the degree here, and I can see that there will be 4 total roots. So go 1, 2, 3, 4. Once I have all 4 of them, I know I'm done. So what I might want to do, before I start testing things, is figure out how many of those will be positive and how many of those will be negative. So remember, the positive roots are determined by the number of sign changes. So in f of x, all terms are positive, so there are 0 sign changes, which means there will be no positive roots. So there's no need to test any positive numbers when we go through trying to find the zeros. And then as far as negative roots, then I can see that if I do f of negative x, remember anything with an odd sign changes its sign, odd exponent changes its sign, anything with an even exponent stays the same. So that actually stays x to the fourth plus 5x squared plus 6. And there are 0 sign changes, which means there will be no negative roots. Let's see. Thinking back to the Descartes' rule of signs, that's for the number of real roots. So there will be no positive real roots, I should have said, and no negative real roots. Since there are no positive real roots and no negative real roots, that tells me there are no real roots whatsoever. So when I look in my list up here, it's going to have 4 roots, but none of them are real, which means all 4 of them are going to be imaginary. So there's actually no need for me to list the possible roots and test any of them, because when I list possible roots, those are all rational, and rational roots are real. So I can kind of skip that step and move on to a different technique. So when we come across this situation, the best strategy to use is going to be to factor. Since there are no real roots, we will switch techniques and we will factor. So we're going to factor x to the fourth plus 5x squared plus 6. And again, we can do the AC method. So we take the first times the third, 6x to the fourth, and I need a pair that would multiply to give me 6x to the fourth, but add to give me positive 5x squared. So let's see, my possibilities would be x squared times 6x squared, or 2x squared times 3x squared. X plus 6x squared would be 7, so the one that's going to work would be the 2x squared and 3x squared. So then I rewrite this term using those. So I have x to the fourth plus 2x squared plus 3x squared plus 6. Group these two together. I can take out an x squared. So I'd have x squared plus 2 left. Group these two. I can take out a positive 3 and have x squared plus 2 left. So then that would factor to x squared plus 2 times x squared plus 3. So that is now my function, x squared plus 2 times x squared plus 3. And then I can go ahead and set each of those equal to 0. X squared plus 2 equals 0. X squared plus 3 equals 0. And solve. So subtract 2 over x squared equals negative 2. Take the square root of both sides. X equals plus or minus square root of negative 2, which becomes plus or minus I square root of 2. So there's 2 of my roots, I square root of 2 and negative I square root of 2. And then do the same thing here. So x squared equals negative 3, which means x would be plus or minus square root of negative 3. So plus or minus I square roots of 3. So there's my other 2 roots, I square roots of 3, negative I square roots of 3. Now, if the question asks me to find all the roots, then I would be done. But if the question asks me to go further and to write the function in fully factored form, then I could rewrite my function using those 4 roots. So f of x would be x minus I square roots of 2, x plus I square roots of 2, x minus I square roots of 3, times x plus I square roots of 3. Now, there are times that we're interested in each of those, actually. These down here are called linear factors with complex coefficients. So each of these are called, all four of these, are called linear factors with complex coefficients, because there are complex numbers in those factors. If the problem is wanting you to factor over the complex number system, then that's where we would land. We would have these with i's in them. But if the question wants you to use real coefficients, then we would stop here, because the rest of the problem gives us imaginary numbers. And these two, this one and this one, are called irreducible quadratic factors with real coefficients. So if you were asked to factor with the real number system, then you would go here, because when you go further, they have imaginary numbers. If you're asked to factor over the complex number system, then you would go all the way down to where you have i's in your number. It is possible to have one of these be real and one be imaginary. Like, say this was x squared minus 9, then that would give me real numbers. So be careful if you're asked to give real numbers that you don't break it down if it has i's, but you do break it down if it doesn't have i's. Okay, well, let's run through one or two that are a bit less complicated. They don't have all those imaginary numbers necessarily, although this one's going to. So this one's going to be another one with imaginaries. This one's going to be like more of a what you would normally see, where you do have some real numbers. So let's look at how many roots we're going to have. So the degree is 4. So we'll have 4 roots. 1, 2, 3, 4. And let's look at the number of positive roots and negative roots. So positive real roots, we have 0 sign changes, so there are none. Let's look at negative real roots. So we need f of negative x. X to the 4th won't change, x squared won't change, and 9 won't change. So there are also no negative real roots. So when that happens, remember we have to kind of change our strategy, and we're going to factor. So we'll factor. So we need the combination that would multiply to give me 9x to the 4th, but add to give me 6x squared. So that is going to be, let's see, f of x equals x to the 4th. 3 times 3 would be 9, and 3 plus 3 would be 6. So 3x squared plus 3x squared plus 9. And then group these. So f of x would be, I can take out an x squared, and that leaves x squared plus 3. And in this group, I can take out a 3, which leaves me x squared plus 3. So f of x would be x squared plus 3 times x squared plus 3. Now when I set each of those equal to 0, x squared plus 3 equals 0 gives me x squared equals negative 3. So x would be plus or minus square root of negative 3, which is plus or minus I square roots of 3. So I have I square roots of 3 and negative I square roots of 3. And then look what happens if I set the other parenthesis equal to 0. I'm going to get exactly the same thing. So that tells me that I have, I could list I square roots of 3, negative I square roots of 3 again, or I could just say that I have a multiplicity of 2 on each one. And then my 3 and 4 are already taken care of by the multiplicities up there. So I have found all of the roots. It asks me to factor it completely. So if it wants it factored over the real numbers, so factored over the real numbers, I would quit there. But it want me to factor it over the complex number system. Then I would have f of x equals x equals I square roots of 3 would give me x minus I square roots of 3, and it's a multiplicity of 2, so that would be squared. And then x equals negative I square roots of 3 would give me x plus I square roots of 3 with a multiplicity of 2 would be squared as well. Okay, find all roots of 2x cubed minus 8x squared plus 9x minus 1. So let's look at the total number of roots. Since the degree is 3, we're looking at 3 roots. 1, 2, 3. Let's look at positive real roots and negative real roots. So positive real roots, we go from positive to negative. So there's 1 sign change. Negative to positive, 2 sign changes. Positive to negative, 3 sign changes. So 3 sign changes tells me I could have 3 positive real roots, or I could have 1. Negative real roots. So I'm going to do f of negative x. So the odd exponents change their signs. So that would be negative 2x cubed. The even ones don't change, so negative 8x squared. The odd ones do change, and the constant term does not change. So I have no sign changes, so I would have 0 negative real roots. So when I go to do my list, test, and rewrite, there's no point in testing any negative real roots because I know I'm only going to have 1 or 3 positive real roots. So I will list my possible rational roots. So it would be factors of 9. So 1, 3, and 9 over factors of 2, 1 and 2. And then when I split that apart, I'll have plus or minus 1 over 1, 3 over 1, 9 over 1. And then use the 2. So 1 over 2, 3 over 2, 9 over 2. Again, I don't need to test any negatives because there are no negative real roots. But then I could test using the positive values. So in my test step, I just use the coefficients. So 2, negative 8, 9, negative 9. I think I'll do my shortcut for synthetic division and only test positive numbers. So my first one is 1. Bring down the 2. 2 times 1 is 2, plus negative 8 is negative 6 times 1, negative 6. Plus 9 would be 3 times 1 is 3, plus negative 9 is negative 6. So that is not a root. Let's try, my next number is 3. Bring down the 2. 2 times 3 is 6, plus negative 8, negative 2. Negative 2 times 3 is negative 6, plus 9 is 3. 3 times 3 is 9, plus negative 9 is 0. So here I have x equals 3 is a root. So x equals 3 is one of my roots. And then I'm going to go to the rewrite step. So it goes list, test, rewrite. And I rewrite my function as the quotient row, so 2, negative 2, 3, remembering to decrease by a degree. So 2x squared minus 2x plus 3 times what I got for my root, turn that into a factor. So x equals 3 would turn into x minus 3. And then since my quotient is quadratic, I will either factor it or use the quadratic formula or complete the square. I think I will use the quadratic formula. So I'll have x equals the opposite of b. So 2 plus or minus square root of 2 squared, well, negative 2 squared, which is 4, minus 4 times a, which is 2, times c, which is 3, and then all over 2 times a, which is 2. So that gives me 2 plus or minus the square root of, inside the discriminant, that would be 4 minus 8 times 3, 24. So negative 20 all over 4. So that is 2 plus or minus 20 breaks down to 4 times 5. So I would have 2i square roots of 5, and then it's all over 4. Since each of those are divisible by 2, that gives me x equals 1 plus or minus I square roots of 5 all over 2. So my last two roots will be 1 plus I square roots of 5 all over 2 and 1 minus I square roots of 5 all over 2. If they, since they told me they wanted me to factor completely, let's assume they mean over the real numbers. So then I would just split this into 1/2 plus or minus square root of 5 over 2i, like we did when we worked with complex numbers. And then we would factor it as x minus 3. I'm having problems with disk space, so if this is a little bit weird, I apologize. We'd have x minus 3 from our first root, and then we're just going to subtract over the 1/2. So x minus 1/2, subtract over the square root of 5 over 2i for the plus 1, and then we'll add it over for the minus 1. So then it would be x minus 1/2 plus square root of 5 over 2i. So this would be fully factored. If they wanted it factored over the real numbers, that's this guy. This is factored over the real numbers. This is factored completely over the complex numbers. Hopefully I have my memory issues for my Chromebook resolved and we can get through this last problem. What we're going to be doing is finding a polynomial that has integer coefficients with a degree of 3 and roots at -3 and I plus 1. So what we are given is that we have a degree of 3, which means there have to be 3 roots. So 1, 2, 3. They've only given us one root at x equals -3 and a second root at x equals 1 plus I. What they don't tell you, but they assume that you are going to remember, is that complex roots always go in conjugate pairs. So that's where we're going to get our third root, because they told us 1 plus I, so we also have to have x equals 1 minus I. So if you don't remember that they go in conjugate pairs, then you'll be wondering where that third root's going, where it's coming from and what it should be. So that frequently happens. It also happens if they would tell you x equals square root of 3, then you'd have to remember you have the conjugate pair, x equals negative square root of 3. So we're going to take our 3 roots and we're going to turn them into 3 factors. So when we turn them into factors, those are the things that go back into parentheses. So we move that 3 back over to the side with the x, and we'll have x plus 3. Then we move the 1 over to the x, so it'll be x minus 1. Move the I over, minus I. And the same thing here. Move the 1 over, so it's x minus 1. Move the I over, so it becomes plus I. So we're going to take our 3 factors and we are going to put them back into function form by multiplying them. So x plus 3 times x minus 1 minus I times x minus 1 plus I. Now, since it says we have to have a polynomial with integer coefficients, that means we're going to have to multiply all that stuff out before we can answer that question, because it's going to have a polynomial. My strongest piece of advice to you is, even though we're going to be multiplying all 3 of those together, what you want to do is FOIL the ones that are conjugate pairs with each other. And do that first before you do any other multiplying. So you can do that either by distributing the x to all 3, then the -1 to all 3, then the -I to all 3. Or you can use that like super foiling box that we used in Algebra 2. That's how I prefer to do it. So I'll do the box method down here. X minus 1 minus I, x minus 1 plus I, and then just create that little grid. So when you get your grid filled out, then you're going to combine like terms, knowing that plus ix and minus ix and plus I and minus I cancel each other out, and negative I squared becomes plus 1. So that would FOIL to be x squared minus 2x plus 2 from the 2 conjugate pairs. And then we still have times x plus 3. And then we are going to need to FOIL this again, which I will do by that superbox method. So you're going to have to pause the video once that comes on, because I'm going to have to pause mine because I'm running out of time. So here is that super foiling box. Then you'll combine your like terms. So at the end, you should have x cubed plus x. So when you combine your like terms, you'll get x cubed plus x squared minus 4x plus 6. And that would be the polynomial with integer coefficients that has a degree of 3 and roots at the 2 listed plus the one that was hidden because it was a conjugate pair. I apologize for the quality of this recording in general. My Chromebook ran out of space like a bajillion times. So be prepared to ask questions when I return to class tomorrow.